Okay, so let's first review what we had done last week. If you remember, we started with the Coulomb law. Which basically stated that if you have two charges separated by a distance r, the force between the two is given by a constant times the product of the charges divided by their separation squared, and the direction is along the line joining them. Now it's important to keep what this r refers to. Most of the time we use the r to denote the position of an object relative to our reference point. In this equation, r is not the position of the object relative to our reference point, but r is a vector pointing from the charge that is exerting the force toward the charge that is feeling the force. So if you, let's say, this is the Q1, this is Q2. If you want to write the force F that Q1 is feeling due to the charge Q2, this is the vector R. And r hat is nothing but a unit vector pointing in the same direction. So r hat is this one. So just like in last year in 109 in mechanics, we in fact had just a single fundamental equation, and everything else we did was based on that three laws, let's say, three Newton's laws. In electromagnetism, we will have like four fundamental equations governing the properties of the charges and electromagnetic fields, and this will be one of them. In electrostatics, this will be our fundamental equation, and everything else we will be deriving from this equation. So it's important that you understand what this equation means. And then we also define one more concept, the electric field. We said that the electric field at a given point is nothing but you put a test charge over there, let's say Q prime, you measure the force that that Q prime charge feels at that point, divided by the charge, and of course you assume that the charge should be small enough so that you don't change the system by putting this Q prime charge over there. So this is the electric field at a point, let's say, R. So this is the force that the charge Q prime feels when you put it at the position R. Again, I repeat, this R over here is the position of the object relative to some coordinate system that you have chosen. Whereas this R over here is nothing but the relative position of the charges. Don't confuse the two R. And we had also derived the electric field for a point charge. If you just use the Coulomb law, we had seen that the electric field for a point charge was given by the E is equal to 1 over 4 pi epsilon 0 Q over R squared in the R hat. And again here, R is the position of the point at which we are evaluating the electric field relative to our charge. And we also studied the infinite wire. So we had this infinite wire with a linear charge density lambda. We had seen that if you consider this point, the electric field is pointing away from the charge if lambda is positive, and it will be pointing toward the charge, toward the line of charge if lambda is negative, and its magnitude was given by 1 over 2 pi epsilon 0 lambda over r. We had the infinite wire example, and now we studied the electric dipole. And a dipole is nothing but two charges. At this point, and if assuming we are sufficiently far away, if L is much larger than D, we calculated that this was the direction of the electric field, and the magnitude of the electric field was 1 over 4 pi epsilon 0 P over L cubed, if I don't remember wrong. And we also studied the other case when we had this dipole over here, plus Q minus Q. We considered this point, the electric field at that point was pointing upward. This is the electric field. Again, this distance from the center we call L, and the magnitude of the electric field was 1 over 2 pi epsilon 0 P over L cubed. So these are basically the summary of what we had done on last week. Now, any questions about these or any other thing that we discussed last week? So this was the question, right? So we have an object that somehow we charge positively. And then we have a sphere. If we just have a single sphere, we said that single conducting sphere, conducting means that the charges are free to move. If it's a metal, it will be the negative charges that will be free to move. So when a positive charge appears, the force between the positive and negative charges will be attractive. So negative charges will move towards the positive charge. So there will be an excess of negative charges at the side which is closer to the positive charge, whereas the other side will be positively charged because there will be less negative charges over there. But if we put another conducting sphere, without this second conducting sphere, this side would have been positive. But then if we bring another conducting sphere, that those positive charges will attract the negative charges from this sphere. So negative charges will move towards the positive charges, so they will be balancing the positive charges. But then since the negative charges are moving this way, there is the number of negative charges on this side is now lowered. If there is less negative charge than positive charge, then that side will be positively charged. So the reason why this side is positively charged, this side is negatively charged, is that all the negative charges in both of these conductors will be moving towards this side. Okay, just one reminder, by the way. For about 1 month or so, we will be studying electrostatics. We will not be dealing with how these charges are moving from this point to the other point, but we will be looking at the systems after all the charges settle in their equilibrium point. So the charges will not be moving anymore. We will ask the question of how long does it take for the charges to go from one end to the other end, for example. Those kind of questions you might be able to ask towards the end of this semester, but not yet.
So what's the shelter?
We will come to that now. Any other questions?
In the last lecture, we talked about the charging by friction.
Okay.
So charging by friction from the microscopic view, is it moving from electrons from one side to the other part, or just organizing the charges like induction?
Well, by friction, you don't have conductors. And you can also charge conductors by friction, but since you will be holding them, all the charges that accumulate, they will just be grounded, they will just go away through the surface. But for example, if you take this object and rub your hand on it, it is likely that there will be some charge on this part. This will be charged, your hand might be charged. Well, the hand is not, these two combinations is not such a great pair to charge, but what happens is the charge from one of them is transferred to the other one. Well, which one? Well, depends on the chemical properties of the materials. It depends on whether there is dust or not, or whether there is humidity or not. It depends on many factors. So it depends on the material. So, in one environment, when you charge an object by friction, it might be positively charged. In another environment, it might be negatively charged. Well, the details we don't really know. So it's basically a transfer of charges from one surface to the other one. And since if they are not conductors, they will just stay there. They cannot go away.
Is that the reason? Because some part, when I make friction with some particles, it can negative and sometimes it can positive. Is it good? material itself, the other material?
It depends on the material, it depends on the environment, the humidity of the environment. It depends on many factors.
How does friction remove electrons from one object and transfer it to another? Is it because of the heat generated?
We don't generate that much heat.
What happens?
We don't know. I don't think we actually. I don't know, that's for sure. I don't think we have a really clear-cut answer. I can just say that if you remember from your chemistry courses, if you didn't drop out of your chemistry courses, you might remember the concept of electron affinity. So some molecules will have a stronger tendency to acquire electrons than some other ones. So that will probably have at least some effect on which materials are charged negatively, which ones are charged positively.
In one sphere, we enclose the positive charge object, and one side negative, one side positive. The negative charge is equal to positive charge?
Well, the charge is conserved. So that is another property of the charge. You cannot create a charge, you cannot destroy a charge. Well, in everyday life, when we say that, okay, this part is negatively charged, what we basically mean is that the electrons just move from one side to the other side. So if one electron moves to this side, that means there is one extra electron over here, one less electron over here. So the charge of this side is minus one electron charge. Here is plus one electron charge. So the charge on both sides will be equal. But conservation of the electric charge is more general than that. I mean, we have experiments in which we can create electrons. Or if you think of the beta decay. In the beta decay, what happens is you have a neutron is transferred into a proton, which has a positive charge. But with a proton, we also have an electron, which has a negative charge. So this is the basic reaction in the beta decay. This is neutral. This is charge 0. This has charge, let's say, minus 1. This has charge plus 1. This has charge 0. So even if you, in circumstances where you create electrons, charged objects, the charge is still conserved. So you have to conserve the charge. Apply to this case. So if initially the object is neutral, but then you bring this positive charge over here, so a negative charge is moved to one side, positive charge is left on the other side, overall it should still be neutral. The total charge should still be 0. So that basically means that amount of negative charge should be equal to the amount of positive charge.
Why do objects get the charge by rubbing or friction? Objects, why do we get charged by objects by friction or by rubbing?
So why do they get charged? I don't think we know the details. The basic idea, though, is that by friction you are not the heat, not the average energy, but some regions might acquire some energy, some electron might acquire. I mean, in friction you have the collision of molecules. And in this collision, you might be hitting an electron and removing it from a molecule. And that electron might just end up in a molecule on the other surface. So that might be why you are having the charge transfer from one object to the other one. If you have some free electron freed due to the friction, if there are two different molecules nearby, and if one of them has a larger electron affinity, then that would probably grab the electron.
Does the magnitude of the charge change by the time? Let's say there's a proton right here in the empty space, and then after a while, the magnitude of that will be discovered.
Okay, let me just divide it into two questions. Let's say I charge this thing somehow by friction or by some other means. If I wait for some time, it will be discharged. Now, what happens is, let's say if I charge it negatively, there's humidity in the air, and humidity is basically water. Water is a conductor, so those electrons will eventually be grabbed by the water droplets in the air, water molecules in the air. And they will just move around, they will go to the ground, they will come to you, and the charge will be spread out in such a large surface that there won't be any charge anywhere. So in this case, charge is still conserved. It just spreads out. It's no longer on this object. The other thing is, for example, the proton. Now the proton charge, you see here I didn't write 1.6 times 10 to the power minus 16 coulomb. For me, as a particle physicist, the proton charge is just plus 1. And it doesn't change. Never.
We know that photons, after a while, they distract or lose some energy. Let's say like 1 million years. But
Well, as far as we know, if you just have a proton over here, it doesn't interact with anything. It will just stay there for the age of the universe. It will not change. Nothing will change, as far as we know. The current limits are longer than the age of the universe for a change in the proton.
After all of this, may I ask just, the charge is just a quantity or electron, basically? Because we are all talking about the changing electron or something, but I'm not quite sure.
Now, in ordinary matter, if you just look at this one has, so it's made up of a bunch of electrons, a bunch of protons, and a bunch of neutrons. Electrons carry electric charge. We know that electrons interact electromagnetically. That's what we say, how we know that it has an electric charge. Protons also have an electric charge. Neutrons do not. So the total charge of this object basically depends on how many protons you have and how many electrons you have. It's not just the electron, but also the proton. But if you look at the inside the proton, we have the quarks, and they also carry electric charge.
So it is like charge is carried by a particle, and it's the quantity of the specific particle.
Yes. So the total charge of an object is basically counting how many, at the fundamental level, the total charge of an object is counting how many fundamental charged particles it has. Now we have a handful of fundamental particles. We know whether they have an electric charge or not. So for a given object, just count how many of each one of them. You know the electric charge of each one, so sum them up, and that gives you the total charge of your object. Then there is the question, why does it, let's say, two electrons, why do we have two electrons repelling each other? Why do they exert any force on each other? To this question, we don't have an answer. We don't know. We just know that there is such a force. We know how to describe that force. And we are quite good at describing that force in certain properties of the electron. We can calculate, theoretically, we can calculate it up to 24 digits after the decimal point, and it matches with the experiment. We can measure it, but we don't know why there is such a force. It just seems to be there. Now let's continue with some examples on the electric field. So the electric field of a ring charge. So what we will assume is we have this ring. This time it's not an infinite wire, but just a ring. Again, it has a charge density lambda. And what we are interested in is if you just draw this line that goes through the sensor perpendicular to the plane of the ring. Let's say it has a radius r. This line is perpendicular to all the radii. and you want to find the electric field, let's say, at this point. What is the electric field there? Again, this is not a point charge. For a point charge, we know the law of the electric field, so we could have just written it down. This is not a point charge, but we can still write it down as a collection of point charges. So we can just divide that object into very small parts. Now, each one of these very small parts, let's say this one over here at the top, creates a very small electric field at that point. And that electric field will be along this line. It's just for the purpose of sketching, let's just assume one is positive. So this will be the very small electric field created by this segment over there. This one. Now there's a symmetric, diametrically opposite segment, this one. It will also contribute to the electric field, let's say this segment. It will also contribute. And the electric field, that symmetrical segment, will be this one. So this segment creates an electric field in this direction. This segment creates an electric field in this direction. Now this distance and this distance, they are equal because these distances are equal. This distance are equal, so these two triangles are in fact they are identical triangles. So this length and this length, they are also equal. But the electric field, the magnitude of the electric field depends on two things: the magnitude of the charge creating it, and the distance from that charge. The distance of this point from these two segments are equal. And if we assume that we divide this ring into segments of equal length, the charge in each one of these segments will also be equal. That means the magnitudes of the electric fields created by those very small segments will be equal. So the magnitudes should also be equal. Now, I have these two vectors that have equal magnitudes. If I sum them up, I just obtain a vector in this direction. It's in the horizontal direction. So just like in the example of an infinite wire, if you remember our example of the infinite wire, we had, if we are looking for the electric field at this point, if we take one segment over here, there was a symmetrical segment on the other side, and the sum was the sum of the electric fields created by both of them. It was horizontal. The vertical components, they just cancel. It's like exactly the same phenomena here. We have this electric field which has a vertical component pointing upward, and this electric field which has a vertical component downward. And since they have the equal magnitudes, these angles are identical, so the vertical components, they just cancel. Whereas the horizontal components, they just add up. Well, this basically tells me that I don't need to worry about the vertical component of the electric field. It's enough for me to calculate the horizontal component of the electric field only. That will be the only component that will remain. So let's write dE. Let's say this is the x, this is the y. I know that dE, it will have a component in the x direction, which will be the magnitude of dE. Let's say this angle is theta, or this angle is theta. They are the same angles. dE times cosine theta in the x direction plus something in the y direction. I don't really worry about the y component because, as we just argued, when I sum all the electric field, it will just cancel. Now, the magnitude of the electric field is just, we have this constant 1/4 pi epsilon 0. We have the charge creating that dE. Let's say this is a very small segment. of length dl. So let's say it has a length dl. So the charge of that very small segment is nothing but lambda times dl. Because lambda is nothing but the charge per unit length. If we have a length dl, the total charge in that length is nothing but lambda times dl. So if we come back to the electric field, okay, this is a constant. Then we have the charge, which is lambda times dl, divided by the distance of this point from that segment. Well, this is the radius. Let's just call this L. If this distance is L, the distance of the segment from this point is nothing but r squared plus L squared square root. Well, the electric field is the square of that distance. So this is my dE. Now cosine theta, this angle over here, but we said that that angle is also this angle over here. But cosine of this angle is nothing but L divided by this length times L over square root of r squared plus L squared in the exact direction. This is the electric field created by this small segment over here. The horizontal component of the electric field created by this very small segment. But it's also the same for this one. In fact, it is the same for all the segments that we can consider, the horizontal component. Because if I even consider a segment on this side, its charge will be the same, lambda dl. This is just a constant. Its distance from this point is the same. L is the same for this point. So nothing would change for the horizontal component. The vertical component would of course be different, but we don't need to worry about the vertical component because they will all cancel eventually. Now the total electric field would be just the sum of all these very small electric fields. Let's say lambda is just a constant. Whether I consider this segment or this segment, is just the same lambda. This is the same. These are all identical. And so these are all the same, so I can just take them out of this segment. Now what remains is this dl. It is the length of each one of these segments. If I sum the length of each one of these segments, eventually what I obtain is nothing but the circumference of the ring. So this sum, okay, this 1 over 4 pi epsilon 0, I can just take it out. Lambda I can take out. L I can take out. R squared plus L squared to the 3 halves. 2 over here, 1 over here, 3 square root. And if I sum dl, I end up having the circumference of the ring. That is 2 pi r in the x direction. Now when I take this sum, the vertical components, they just cancel. So I don't have this plus the other terms. They are 0. Or let's write the electric field. Okay, this 2 pi would cancel this one. What remains will be 2. 1 over 2 epsilon 0 lambda L r over r squared plus L squared to the power 3 halves in the x direction. This is the electric field of a ring. Or we can also write this as 1 over 4 pi epsilon 0 lambda q L over r squared plus L squared raised to the power 3 halves. Now 2 pi r is the circumference. If we multiply it by lambda, lambda is the charge per unit length. So if I multiply the charge per unit length with the total length of the object, that would give me the total charge of the object. Q is the total charge. Oh, sorry. Q is the So Q, total charge of the ring. So we have the total charge of the ring multiplied by the distance from the center divided by the r squared plus l squared to the power 3/2. Now, any question on this one?
Could you write again the equation of lambda?
The equation for Q. For lambda. This one. Now I just looked at this one. Lambda times 2 pi r is just Q. Q is equal to 2 pi r times lambda. This is the definition of the lambda, you can say. Okay, lambda is the total charge divided by the total length. Well, integration is nothing but summation. I summed over them. That is integration. I already integrated. I integrated over all these segments. Any other questions?
The outcome it's not zero. You consider that it's DE plus DE.
DE plus DE prime.
Right, from the upper part and the lower part.
Yes.
Right? But when we are calculating, we cancel this and dealing with it as super fields, right?
Now, what we did was, well, we had an argument up to this point. What we said was, if you take any segment, then there is a diametrically opposite segment.
So it's 2D.
If we sum these two DEs, the vertical components cancel and we end up with the horizontal component.
So the one part, the lower part is multiplied by 2. It's not between.
Well, if you are summing both of them. Yeah. Yes. Now, but when I'm summing over here, after this argument, what I did was I just considered one of the segments only. I looked at one segment. I just ignored the vertical component because I know that when I sum over all the segments, I will be summing this one with this one, this one with this one, this one with this one. I will be summing over all diametrically opposite segments, and I know that this component will cancel because of this argument. So I just keep track of the horizontal component, and I sum the horizontal components of all the segments. In this sum, there is already this segment, and there is already this segment in this sum. And that gives me 2 pi r for the DL, and that is where we are integrating. The sum over DL is nothing but the integral over DL, and the integral over DL just gives me the circumference.
What if the point charge having the center mass? Check it out with the
Well, that will be a nice homework after some point. I'm not so mean as to give you that homework yet. There are simpler means of calculating the electric field. Any other questions? Well, there is no force because there is no charge at the point P. I didn't put a charge over here. There is only this charge. And I'm calculating the electric field over here. Now, if you put a charge over here, that charge would feel a force. And that force will be the electric field multiplied by the charge that you put over here. If you want to have the force, you have to put a charge. Electric field is not a force. It is related with the force acting on a charge that you put at that point.
So I think that this question is a 3D question. Actually, it is a 3D question because it has some
Sure.
component. should have stated that as a general party is not just like
Okay. So if this makes you happy, fine. No problem.
I don't, that's not just what I meant. When we say TV, also has a which also is
True.
body inches just to precise. Because I know that if I did something like this in the exam, I'll get like minus.
Probably.
Yeah.
Any other questions? Well, if you have more questions, you can keep it until the next hour. Well, there's a small survey that the psychological assistance unit wants to carry out. Unfortunately, it's in Turkish. So for those who don't speak Turkish, you can take a break early. I'm afraid. I mean, it's not obligatory. It's anonymous. You don't have to write your name, etc. Yabancı öğrenci lazım.
Arkadaşlar, çok kısa bir vaktinizi alacağım. Ben psikolojik danışmanlık ve rehberliğinde doktora öğrencisiyim. Üzerinde çalıştığımız konu aidiyet duygusu ve sosyal doyumla ilgili olan bir şey. Özellikle ülkemizde son zamanlarda yaşanan durumlardan sonra özellikle okumuş kesimin aidiyetini merak ediyoruz. Ne kadar acaba bir şeye daha bağımlı kaldığımız, umut düzeyimiz, bu gerçekten önemli bir konu.